Hello, I'm Jungwon Park, and I would like to introduce our paper, Enhancing Intrinsic Features for Debiasing via Investigating Class-Discerning Common Attributes in Bias-Contrastive Pair. In the presence of dataset bias, image classification models tend to rely on bias attributes that are spuriously correlated with a target class when making prediction. For example, if most samples in the vision class have water surface, the model will rely on the bias attribute, water surface, instead of the intrinsic attributes, such as the action of holding the vision rod for predicting the class. As a result, the model only predicts the samples with water surface correctly, failing to correctly predict the samples without the water surface. In this example, the samples with water surface are bias-aligned samples, and the samples without water surface are bias-conflicting samples. We will call them BA and BC samples for short, respectively. Debiasing aims to encourage classifiers to learn intrinsic attributes that inherently define a target class rather than focusing on the bias attributes. In this paper, we present a debiasing approach that provides the model with explicit spatial guidance on intrinsic features while not using bias labels. The intrinsic features in the unbiased dataset can simply be identified in generally appearing features in the training samples. However, generally appearing features in the biased dataset inevitably include biased features as shown by the red lines. Therefore, we identify the intrinsic features in the biased dataset, which is shown by the yellow lines, by investigating the common features between a BA and BC sample. We name this pair as bias-contrastive pair. Our framework consists of a biased model of B that focuses on biased attributes and a debiased model of D that learns debiased representations. As we mentioned before, we need bias-contrastive pair to identify the intrinsic features. As the majority of the trained data are BA samples, our goal is to mainly adopt the BC samples as an auxiliary input XBN. To achieve this, we first construct the candidate dataset DCAND-BN. The samples that are incorrectly predicted by the majority of the pre-trained biased models are regarded as the candidates of XBN. During the training, we dynamically update DBN every iteration to mainly adopt BC samples from the candidate dataset DCAND-BN using the bias-negative score. The bias-negative score further encourages BC samples to be adopted by filtering out the samples with decreasing alpha loss, which are mostly BA samples. XBN is sampled from DBN to construct a bias-contrastive pair. Using a bias-contrastive pair X and XBN from the same target class Y, we provide explicit spatial guidance G of Z for a debiased model of D to learn intrinsic features. G of Z highlights intrinsic features, and the guidance loss encourages the model to learn the intrinsic features by minimizing the distance between G of Z and Z. To achieve this, we introduce the intrinsic feature enhancement weight, which is IA weight, that imposes a high value on the intrinsic features. The IA weight identifies the region of intrinsic features from bias-contrastive pairs by investigating their common features, C of Z, and class-discerning features that are relatively underexploited in the input, R of Z. Our method achieves state-of-the-art performance under both synthetic and real-world datasets with varying degrees of bias. This figure illustrates that our IA weight effectively highlights the reasons of intrinsic features. This is the end of my presentation. Thank you for listening.